So you grew up in the 40s and 50s, right?
Correct.
Outside of Boston.
Yeah.
And
Not very far outside of
not far outside. Okay. So I was wondering, when was it that you first became aware of mathematics, and what attracted you to it?
Well, I started thinking about mathematics very early, although I didn't think it was mathematics. I thought it was just something that was fun to do. So I learned quickly all the powers of 2 and was pleased to remember them up to, I don't know, 2000 and whatever. More interesting, I think, was I discovered Zeno's paradox very early when my father told me, to my horror one day, that a car could run out of gas. And I was really very little. I was down at the beach. I remember very well where I was. And I started thinking to myself, well, how can it, after all? It could always use half, and then use half of that, and then only half of that, and so on, so that would really never run out.
So you weren't kidding when you said you discovered it?
Yeah, I didn't think through the whole problem, that perhaps, but you'd never get anywhere either. But nonetheless, I just thought of that continual dividing and leaving a little and dividing and leaving a little.
You were how old then?
Oh, 3 maybe, 3. I knew about half.
That's impressive.
Yeah, I mean, it was in retrospect. And then one other thing that I remember very well is lying in bed. Now I was somewhat older, but maybe 10. And contemplating the question, the statement, pass it on. Now, you know, when you say to someone, pass it on, we all intuitively know what that means. But I lay in bed trying to define it precisely. And I think you actually need induction or something like that. But at one night, I distinctly remember falling asleep very satisfied. I had finally completely defined pass it on. But when I woke up, I didn't remember exactly what my definition was.
Yeah, this is a well-known experience.
And I think I sort of got off that topic after a while. So, but those were mathematical thoughts. So, you know, I always liked math in school. I wasn't terribly good at arithmetic. And I remember distinctly having trouble with long division, remembering the algorithm. But on the other hand, all the ideas were very appealing to me. I didn't know there was a career as a mathematician. I just, you know, liked that stuff.
But did it have some special appeal? Did you think of it as something that was different from any other thing?
It was just something I thought about a lot. I mean, you know, when I learned formulas for volumes and surface areas in the 8th grade, I remember, you know, being very pleased with those formulas. I didn't know how to derive them, but I was pleased that they existed. You know, the formula for the 4/3 pi r cubed or whatever for the volume of a sphere. I thought, that was pretty good. So by high school, I knew I was going to be a scientist of some sort, but I just assumed mathematics. I liked math. I didn't like chemistry. I didn't like physics particularly. I didn't understand why it was, what it was all about in a certain sense. But the math was always very clear. I loved playing geometry. I loved learning about proofs and that sort of thing, and spent a lot of time contemplating these various geometry problems.
Did you think that proofs was something that was just special to geometry, or did you understand that they played a role elsewhere in mathematics?
At first I thought it was just special to geometry. Then I learned sometime in high school that no, there are various things to be proved and so on, and definitions. I loved it all. I mean, I really liked that all. And contrary to the wishes of my doctor, who felt that any Jewish boy who was smart at science, math, whatever, should become a doctor, and I couldn't imagine being a doctor. I insisted I would major in mathematics, and still, without really knowing what it was. I mean, I thought it was kind of like, well, whatever. And I, you know, went to MIT and skipped the first year of math and started in the second year. But and I was okay, but at the end of my freshman year, the second semester, I took a graduate course. It said self-contained. It was an algebra course. And it was a very interesting experience because I managed to get through the course, but I didn't really, I was 18 years old. I didn't really understand what it was all about somehow. I mean, you take the fundamental theorem of homomorphisms. Why would you want to make these sets into elements of a group? What was the point of it all? And then that summer, I read some more algebra, just because I thought I should learn some more. And somehow, within weeks, I remember everything became totally clear. It was just all obvious. It was great. I loved it. I went on and took a lot more algebra, follow-on graduate courses in my sophomore year, Galois theory, all that stuff. It was all terrific. And then took a topics in algebra course with Iwasawa in my junior year, which was completely intense. Sometimes I just couldn't get something at first, and it would be very mysterious to me, and then it would click in. And maybe that's typical. I don't really know.
When did you start to get that feeling that mathematics was maybe in some ways more real than other things, or perhaps had a timeless quality, or perhaps because you prove things or discover things, that it had that special something about it?
I'm not sure that I conceptualized that notion of the permanence or the reality of mathematics until I was asked that silly question, which I'll recount again. But mathematics was my life for those years. It was so it seemed, the most natural thing in the world to be always thinking about mathematics. And so when I did leave the field after about 20 years in my late 30s, and some business guy, I guess, and I went into business, and a business guy said to me, well, how do you like the real world? Kind of joking around. And I said, well, somehow it seems to me that something like the integers has a great deal more reality than some McDonald's stand or whatever. That's here today and gone tomorrow, and the integers are forever. So I think I implicitly, if not explicitly, I think like most mathematicians, felt that these concepts were really of an eternal nature. And so that was my notion.
Do you think that there was anything that was important about just being a kid in developing into, being a mature mathematician who actually did research and so on?
Well, I wasn't brought up in any special way. There were things about my nature that I think lent itself to doing mathematics. Some mathematicians are very fast thinkers, and then they can solve a problem lickety-split, and I'm not one of those. But I do have a capacity to just contemplate things. So they were very worried, my mother told me later, when I went to nursery school. I started nursery school, and there was a tree in the backyard. I'd never had an opportunity to climb a tree. And for weeks, as soon as we got out to play, which was most of the time, I would climb that tree, sit on a branch, and watch everybody and think. This was apparently very unnatural. And they were concerned, and my mother told me that I can't sit in that tree anymore, Jimmy. You have to play with the other children. And I was just fine, I'd play with the other children. But I just enjoyed sitting there thinking. So I was an only child. So I didn't have a brother or sister to chat with all the time. So I did have the capacity just to think, and I sometimes talked to myself, as it turned out, because some of my friends were amused to see me standing talking to myself. So I think that's a quality that, not talking to yourself particularly, but a quality of just being able to get lost in thought that is pretty good for mathematics.
So if we go back to the time that you were at MIT, which includes also part of graduate school, right?
Yeah, because I graduated 1 year early, and then I stayed 1 year as a graduate student.
What was the process like for you going from being a student to becoming more of a mathematician? Although I remember you're having told me, like, when you get your degree, you're not a finished product. But there's some kind of transition that takes place, and what was it like, sort of mentally and psychologically?
It was pretty seamless as far as I could see, because as I got more and more into mathematics, I felt like more and more of a mathematician. So in some sense, I feel I became a mathematician at about 18 when I was starting my sophomore year, and it was a great year for me learning mathematics. I learned a lot that year, and I just felt like, like I was immersed in this subject. I didn't have any ideas for new mathematics until, I guess, my third or fourth year. Maybe it was in that graduate year. And I remember my first wondered about and how to deal with it, and that is why the product of harmonic forms was not harmonic. It seemed a pity to me. And so I started thinking about, okay, what can one say about this question? But I remember in my thesis, which when I was a junior, I had to write a graduating thesis. It was Ankeny. And I had an idea of something.
What was it about?
It was about linear algebra within a products, the orthogonal group, stuff like that. And reflections and rotations and how you build things with fields other than the reals. And I had an idea how to prove something. I had an idea. This should be true. So I guess that was another mathematical idea. And I think, like a lot of people, I remember exactly where I was when I realized what the trick was to proving that. I was sitting in a movie that they played at MIT. There was a movie club. You could go and watch movies. And I was sitting there and, and we all remember those moments. So I remember that one. But I just sort of eased into it and I felt I was a mathematician.
So did you have particular mentors or role models? And what did that mean? People that inspired you, or you thought you wanted to be like them? That there was something cool about it, or anything like that?
Certainly there were people who I found very inspiring. I don't think I ever really wanted to be like anyone. It never occurred to me, if I could only be like so-and-so, I would be happier. But Singer was very inspiring. Ambrose was very inspiring to me. I don't know if you remember Ambrose.
I remember him a little bit.
Ambrose was, they encouraged me.
People who knew Ambrose seemed to think very highly of him.
Yeah, he was a good teacher. He had very strong opinions. So he was helpful. Singer was helpful. I had another thought at that time. So I ran into Barry Mazur. Now, Barry Mazur, I graduated at MIT in 3 years, but Barry Mazur graduated at MIT in 2 years. He was quite famous. And I ran into him on the street, and I had just met him in some other context. I don't remember what. Well, I do, but it's not important. And I ran into him late at night in the street. And as I recall, which is probably wrong, but I somehow recall his wearing a pink torn T-shirt. And I was telling him that I was learning Galois theory. And I really liked that. And he said, "Oh, it's so beautiful." And he waxed about Galois theory and this and that.
Yeah, one can imagine it.
Yeah, and I remember thinking, okay, this guy is undoubtedly better than I am. I figured, okay, I've met a guy who's better than I am. But it didn't bother me in the least because I felt, okay, I may never be as good as this guy, but I think I can do some good mathematics and have a satisfying experience. But like a lot of kids, they think, oh, they're the smartest kid. And I always thought I was the smartest kid around. And then, of course, you learn, oh, yeah, maybe you're not the smartest kid around. But it didn't deter me in the least when I came to that conclusion that Barry Mays was probably a better mathematician than I was.
Did you think that maybe in some ways, though, you had something to offer that he didn't?
Oh, sure. Not necessarily that he didn't. I felt I had something to offer, which would be constructive. And whether or not he was maybe even had more to offer in some ways, I don't know. But I was perfectly content with that, and as it turned out, I had some pretty good things to offer. But you know, you learn these things that you're not the smartest guy. None of us is, I suppose, or maybe there's some smartest guy, but even. But it doesn't matter so much, is the point.
What are some of the things you think are important that might not be totally obvious earlier on?
I think good taste is very important. And I remember when I first heard of good taste, because I'd learned what a group was. And I said, oh, a group, so you put two things together, you got another one, and so on. I thought, well, how about if you put three things together? Maybe there's a group, maybe there's a definition. So I made a definition for myself. You put three things together, you got one thing. And then I sort of fiddled around with what do you do about inverses and social. And I had a set of rules. And I showed this to Arthur Maddock, who was I was a freshman at the time, I think. It was in the spring where I was taking this crazy algebra course. And I showed him this, and I said, well, what do you think? He said, He said, do you have any examples? I said, no, it didn't occur to me to have any examples. And he said, taste is very important in mathematics. And now I didn't know altogether what he meant, but I learned. I mean, I think choosing your problems is really important, and trying to do something that you feel is really worthwhile because it will illuminate, truly illuminate something is a good characteristic. And imagination. I think taste and imagination are two very important components, along with at least a decent set of analytical skills. And the better they are, of course, the better you'll do, all other things being equal.
After you got your PhD, we met at Harvard during, if I'm correct, the 1 year that you were a professor there.
Yeah, I was there 2 years, but 1 year I was just on research, and the next year I was a professor. Right.
Okay. So that was my senior year. That would have been 1963-64, when you taught the infamous PDE course.
Hormander's course, that's right.
Yeah, which certainly ruined me for that subject for the next 10 years.
Me too, actually.
You must have had some idea about what you were going to do with it, or maybe not.
I figured partial differential equations should be important. I'll teach a course and learn it.
It should be important in geometry.
Yeah.
That was a great insight, actually.
Yeah.
Because now it's, kind of so common. It's a truism, but it wasn't always so.
Right.
I mean, people like Yao, for example, certainly played a big role.
Oh, for sure.
After a year, you resigned, right, and went to IDA.
Yeah.
Yeah. So why was that?
The family had made an investment, and as a result of that, I had borrowed some money, And in fact, that year that I was teaching at Harvard, that first year, I was also teaching, unbeknownst to anyone, although I had no reason to think I couldn't do this, at Cambridge Junior College. I bet you didn't even know that.
Not even I knew that.
You know, not even you knew that. So instead of teaching 2 courses, I was teaching 4.
This may explain your performance in the PDE course.
Possibly. Well, my performance wasn't that bad. I was always ahead of the class.
A week ahead of.
I was at least a week ahead of the class. I heard that IDA in Princeton paid more, and you could still do mathematics. And
I don't know, should we remind everyone what IDA was all about?
IDA, it's where they hire people to do secret stuff. They hire only mathematicians in codes and ciphers, that kind of stuff. And the rule there was you could spend half your time doing your own research, and you spend half your time, at least half your time, on their stuff. And it seemed reasonable, and I applied for that job and got it. And I was not very happy at Harvard, to tell you the truth. And I was also, my research, I was right in the middle of learning this new field, minimal surfaces, minimal varieties, that sort of thing. It was a time of a little transition in my life. So I went there, got more money, and it turned out it was a pretty good experience.
Yeah, so for one thing, you actually, I think, had a real success there, right? Or you and the group?
You mean in their work?
Yes, which was code cracking.
Yeah,
right?
I solved a problem there that had been around for a long time. The field had some outstanding problems in addition to trying to break some secret code or whatever. There were some problems in the whole, some basic problems in the field, issues, problems, I guess. And I solved one of them. I was very pleased. So my work there was good. I wasn't the best code cracker in the world or whatever, but I was pretty good. Anyway, I solved that problem. But I also did a lot of mathematics.
Was this really your first exposure to statistics and probability as a tool?
Oh, totally, yeah.
How much of its potential did you foresee, or what did you think about it?
You know what I found there, I'd never done anything like this, the code cracking part, and it really amounted to coming up with some attack on a particular problem, and then designing that attack, which would end up being a computer program, and then they would run it. And I was no good at all at programming, and in fact, most of the mathematicians there didn't do their own programming. In those days, we had programmers. You design the algorithm. But I really liked that whole process. I liked everything about it. I liked designing an algorithm, you know, coming up with some attack, designing an efficient algorithm to test it out, and seeing how it came out. I mean, you know, it was like fishing or something. I don't know. Actually, I don't like fishing because I never catch anything. But here I felt we might catch something every once in a while, and it was a lot of fun. I liked it all, and I'd never seen anything like that. So yes, you're right. Later on, that experience of making models, looking at data, making models to try to interpret the data, was certainly learned there. And if I hadn't been there, I think the business that we built later would never have occurred.
I think you were already interested in the stock market, as I recall.
I always had this other interest in this financial interest. You know, even as an undergraduate learning mathematics, I wanted to start a movie theater. And I found a woman with a wooden leg. I'll never forget it. And she was going to be my partner. The only thing is I didn't have 10 cents, so I couldn't figure out how to start this movie theater.
Is it right or wrong that you were interested in applying those methods to the stock market as a possibility at least?
Yes, at IDA I got interested in that, and in fact inveigled some of the people there that we could start a company. That didn't really get off the ground. We came pretty close to starting a company. I had the two best programmers there, and the boss and I, the four of us, we were going to start this company. And I knew a guy who was arranging to put up the money, and we were going to revolutionize Wall Street. At that time, Wall Street had no computers. They did their accounting by card sorting methods. None of it had been computerized or whatever. And there was clear, you could do some research on this stuff. So in the middle of everything, I was trotting around New York. I was 28, I guess, with this money guy making presentations of this company, and we needed X to start. I had a plan. We needed, I think, maybe $1 million, and all we could raise was $800,000. But I'd made this rule: if I can't get $1 million, I'm not going to leave this job and go on and do this. So we never got the $1 million, so we stopped.
What do you think would have happened if you'd succeeded in getting the $1 million?
It's a good question. I don't think the business was that well conceived in retrospect, and I expect it would have failed. Mm-hmm. So it's probably a good thing that we didn't get the $1 million.
Well, maybe it was an idea whose time hadn't come yet.
It hadn't come. So in the back of my mind, it was always, making some money was always of interest to me, but for long periods I didn't think about it at all and just did the mathematics.
So the other thing you were doing while you were there was the minimal varieties work.
Right.
So how did you think about what you were doing while you were doing that? Because for a long time, I think you've told me on other occasions, you were really trying to do basic stuff and formulate things the way they should be formulated and understand it, I think, in a basic way rather than having a goal of solving some outstanding problem.
I had no such goal of solving some outstanding problem. My goal was to understand these objects, minimal varieties, and understand them, and what's the geometry, how do their variations change, what's the right formula for an understandable formula for variation, Jacobi fields, conjugate points, all these kinds of things that you learn about geodesics. I wanted to put into a geometric framework for higher dimensional objects that were, critical points of the area function, or the volume function, whatever. So I just worked along those lines. I looked at examples, Kähler manifolds. I think sub-Kähler manifolds are minimal varieties. Looked at various examples. What happened was I had become friends with Fred Almgren at Princeton, who had solved this plateau problem in the Bernstein conjecture for one level up, one level higher than 2. I guess he had done 3. I don't remember.
Yeah.
But and I looked at his paper, and it mentioned. He said, this thing is a holomorphic quadratic differential, something like this. And I said, holomorphic, I didn't know what it was. I understood, hey, this thing must satisfy, in that case, it satisfies some kind of partial differential equation, linear equation. So then I started playing around with the second fundamental form in great generality and saw, hey, it does. It satisfies a nice set of equations. One of them is an equation that was well known, but the other was perhaps not so well known. And then when
the other was a big breakthrough, I think.
Yeah, and then you
I think I remember when you were working on that, and It was very complicated because you did it in, I mean, it was an involved computation because you did it in generality.
Yeah, I was doing everything in generality.
But I remember you saying that it had to work out.
Yeah, it had to work out, and it did work out. Now I had this equation, and that was, I could see that this was a very good tool. And then I decided, okay, now I'm ready to look at this problem and learn what the Italian school had accomplished. So really the singularities were cones of some sort over a minimal variety in one lower dimension. So that gave a beautiful description of the singularities, and the job was to show that those cones basically didn't minimize, so and therefore could be not resolved, but those critical points didn't really exist in some sense. You wouldn't, you'd slide by them. And then I had an idea of how to construct the right variation to get by that and show it didn't minimize. And
that happened pretty quickly, as I recall, because I was a graduate student, and you were instructing me at that point. Holmgren had influenced you at an earlier stage, what you were describing pre the Simons equation, or at least had told you some facts that were.
Well, he didn't tell me. I just read it, saw it in his paper. He just said, "Here's a paper," and I read that, and I saw this thing, and that's when I decided to try to derive such an equation. And then it was not a very long time, maybe a couple of months before, I don't remember now, I was able to solve this problem up through ambient dimension 8, and my example, my variation worked, but one dimension higher it wouldn't work anymore. A sign that needed to be positive became negative, or whatever.
Yeah, for a particular cone, right?
Yes, I guess that's right. But the general example, when the general process broke down in one dimension higher, now there might have been another variation that would done that. I mean, I had a sample, a way to always go further in the minimization process, but not in ambient dimensions bigger than 8. Then I found this counterexample, this proposed counterexample, so I could see that no matter what you did, any variation in this cone with S3
Infinitesimally stable.
was locally stable, I guess. Yeah, infinitesimally, whatever it was stable. Yeah. And any variation would actually increase area. So, but I had no idea how to prove it was a global minima. It was enough already. So, I had a lot of material, and then I wrote the paper. So that's, what was 4 or 5 years on that.
Maybe not everyone knows the story of how you came to that it came through the combinatorial Pontryagin quest.
Right, which you were involved in.
Yeah, and actually stayed involved in for a long time.
Well, I had come to Stony Brook. I got fired, from that job.
Oh, yeah, I was going to ask you about that. I'm glad you reminded me. So how did that happen exactly?
Oh, it was the Vietnam War, and IDA was a Washington outfit with a satellite in Princeton, but all the rest of it, the Institute for Defense Analyses, it had a weapons system evaluation division. It had these very warlike sounding units. Our unit, the Communications Research Division, sounded very, very harmless.
I think that was the only one that most of the public knew about.
In D.C., the others was a bigger operation. But in any event, and in fact, we had nothing whatever to do with the Vietnam War. We were after bigger game. The IDA was run by Maxwell Taylor, the famous General Maxwell Taylor, who was retired head of chief of staff of the services, whatever he was, and a confidant of Kennedy. And now in his dotage, he was running this IDA. And he wrote a cover story in the New York Times Magazine section of how we're going to win the Vietnam War. we're doing everything right. It's just a matter of time, blah, blah, blah. Stay the course, we'll win it in no time. Anyway, it was a stupid article. The war was a stupid war. And so I wrote the Times a letter saying not everyone who works for General Taylor subscribes to his views. And I gave my own. It was a good letter. I was very pleased, and they published the letter in the Sunday edition. And then I was on the watch list as far as I could tell, although no one said a word to me. No one said a word to me. But
then you couldn't leave well enough alone.
I couldn't, well, that's right, I couldn't leave well enough. Well, someone came and interviewed me. A guy came to interview me about 6 months later, claimed he was doing a story for Newsweek magazine, about people who work for the Defense Department, which I did indirectly, who were opposed to the war. He says, they're few and far between. Could I interview you? What did I know about interviews? So I said, sure, what do you want to know? So he said, well, I see you're still working there for the Defense Department. You're opposed to the war. How do you approach that? So I was kind of a wise guy, and I said, well, they had this rule there. I said, you could spend half your time on mathematics and half your time on their work. And I had elected to spend all my time on mathematics until the war was over. And then when the war was over, I would spend an equal amount of time on their work to catch up, and that would be that. It wasn't even quite true, because I was still finishing up one of their problems. But I was a wise guy. So then I went back to my local boss, and I told him, hey, I gave this interview. He said, what? I said, it's okay, nothing. I didn't say anything, spill any secrets. He said, oh, okay, what did you say? And I told him. He said, okay, I better call Taylor, Maxwell Taylor, tell him about this. So he called Taylor, and he picked up the phone, and he hung up the phone, and he said, you're fired. And that was it. So I was fired. I was astounded at the whole proceeding, but I was fired. And 3 days later, Lyndon Johnson stopped the bombing, announced he was not going to run for another term, and I figured, hey, this whole thing is over. And I went back to this fellow, Dick Leibler, who was the boss, and I said, hey, looks like I was 3 days the wrong side of this thing, because now the whole thing is going to be over, and what's the difference? And he said, I don't think it matters. And so there I was, fired. But I didn't mind it. I had solved this Bernstein conjecture that we just discussed, and so I knew I was going to get a good job somewhere.
How did you suddenly become chair at Stony Brook at such a tender age?
At such a tender age.
After having just been fired.
They were looking for a chair, and had been for 5 years, without success. They were looking at distinguished guys.
So we're talking about 1968.
1968, yeah. Distinguished guys, and none of them had come along, or at least who were willing to be chairman. So they were kind of desperate, in my opinion. And someone suggested me.
You know who that was?
It could have been Lenny Charlap. And it was very appealing. I had already worked out something where I'd be half-time at Columbia and half-time at IBM Research up in wherever they were, up in Yorktown Heights. I thought that would be a nice sort of continuation of what I was presently doing mathematics on one side and IBM. Sounded interesting. I had that lined up.
Did you have any idea of repeating the half and half?
Yeah, well, that was a half and half deal. But then this Stony Brook thing came up, and it was fascinating to me. I had never thought about being a chairman, but they really needed to build up a department, and I like people, and I like to hire people. I like to not hire. I never hired anyone, but I like to work with people and sort of get things going.
So you're already, that kind of thing appealed to you at that time, of building.
Building something, yeah, definitely. Just like when I wanted to start a company a few years earlier, that was, I liked it.
But I guess Stony Brook was your first experience, actually,
sure.
of building something like that. Yeah.
The guy interviewed me, the provost, it was Bentley Glass was his name, and he said something very funny. You know, he said to me, Well, Dr. Simon said, you're the first person we've interviewed for this job who actually wants it. I said, well, I want it. So they took a chance, and it worked out good, worked out well.
I guess it was a reflection of the times that something like that could happen almost. I mean, it was much more support for science. Things were much freer at that time that they could, particularly, I guess, in the state for a little while. There was this idea, they had these big ideas for Stony Brook,
Big ideas
but
for
still
Stony
a 30-year-old guy.
Yeah, well, at the time, I didn't feel so young. I mean, I had 3 children. I had some success. I always felt like very responsible. I take care of everybody or take care of things. So I didn't feel so young. I didn't feel like I'm just a kid here. What do I know what I'm doing? It seemed fine to me. I wanted to understand characteristic classes, and I never really dealt. I mean, I knew the Chern-Weil homomorphism and that stuff. I didn't have a good feel for it, so I thought, okay, I gotta learn this stuff. And so I started fiddling around, and maybe you and I talked relatively early in this proceeding. You came to Stony Brook the next year.
Well, I remember your having come to the famous Global Analysis Conference at Berkeley in 1968. Remember that? It was this huge summer institute.
Yeah, yeah.
And so I remember your having come out there very excited about this problem. So the combinatorial Pontryagin class problem with the idea that you would just do some residue calculation.
Yeah, I figured, okay, the Euler characteristic has a nice combinatorial formula. Why shouldn't the signature? But this was sort of a way to learn the subject. Okay, I get this start with the Chern-Weil formula, and then starting flattening out the pieces and seeing what happens, and it was all very interesting. It was a great experience. Unfortunately, it didn't end up with a combinatorial formula for the signature. I guess it's the first Pontryagin class, whatever it is.
Yeah, say for a 4-manifold.
Pardon me, I just wanted to work for a 4-man. I just wanted to study that. In the course of it, I came up with this 3-manifold number, or this function of a 3-manifold. I guess it was the boundary of the star of a vertex or something like that, and started fooling with that.
So I guess a key point in this is that implicit in what you wanted to do from the beginning were not only the characteristic forms, but the transgression forms, right?
Well, if you're going to start trying to integrate the characteristic forms, you're immediately led to the transgression forms, because locally it's D of those things. So
subsequent development showed they hadn't been given their proper respect. They're just dues. They're props.
That's right. It was a convenient way to lift something to the principal bundle and make it bound. But you needed it to prove the Chern-Weil theory. You needed to show these things are cohomologous, so you need to show they differ by something exact. But the thing itself was not taken particularly.
Yeah, I think it was, thought of as something that came up when you were studying characteristic classes, but not something that was necessarily interesting in its own right, particularly because they weren't closed, of course.
I mean, it's interesting, and universally it turns out they're well-defined up to exact. Yeah. So you usually think of things closed modulo exact. This was just all forms modulo exact. But so they had this property. But sure, I think people hadn't thought about those forms so much. In any event, in the bundle, these forms were restricted to these classical cohomology classes on the fiber. So, because when you restrict them to the fiber, they're closed, and everyone knew about trace powers, or everyone, but it was sort of, that was pretty well known. So, in some setting, the transgression forms had a life, for
No,
sure.
I think, yeah, right. I mean, even in topology, in a way, at least the topological idea of transgression certainly existed. But isn't it fair to say that Chern sort of knew these formulas, but it hadn't maybe occurred to him that
Oh, I think that's right. I think that's
that they were significant as objects in their own right?
When I came to him with a three-manifold result, that here's an invariant of a three-manifold, it's a conformal invariant, and it's only defined mod z, but that's good enough, and then it's an obstruction to something being conformally immersed one dimension higher. He was very excited. He was very excited, and remember the day we were together, and I
You mean on the plane?
on the airplane, and I made that calculation. If something was codimension, the thing was codimension 1 and R4, I said, oh, I can calculate this invariant. It just comes out 0. And you say, yeah, but that's great. I said, oh, maybe you're right.
So what was it like working with Chern?
For him or with him?
I thought I said with him.
I heard for
Did
him.
I misspeak?
Yeah, maybe. He was very up. He taught me some of this more arcane calculus of how to manipulate all these forms, which I, had invariant polynomials, and, in detail how you turn these into characters and all their various properties and so on, which were more than I had known before. And he was very facile at dealing with that stuff. So he'd write down formulas and move the bracket around and so on, and say, you see, this is this, and so on and so forth. So he taught me a lot. And then we wrote our paper together. But already you and I had started doing some work.
Right. Well, I mean, that went back to the approach to the combinatorial Pontryagin also, which didn't, for good reasons, quite work out. But yeah, we had been talking about it for some time, I guess,
Right.
as it developed.
Well, I kept trying to push down these things to the base. You could get certain, what we now, anyway, came to call differential characters, but you could have some functions on the cycles in the base that were well defined, and I gave them a name, and I wrote up that whole paper, and I think even submitted it to the Annals, and I even think they accepted it. But in the meantime, you and I started looking at a more abstract version of this stuff, and then I saw, hey, there's better ways to do this, and I remember calling Singer and said, look, I wrote this paper, I think they want it in the Annals, but I don't think, there's a better way to do it. What do you think? Should I let it get published or not? And he said, who needs a paper that you're going to soon replace? It turned out soon meant like 30 years, whatever.
Well, maybe till it actually appeared, right? We had the famous notes from Stanford from 1973.
But I was, if you ask what, it was a high point in mathematics for me. It might sound silly, but I was so pleased with the definition of a differential character. I was really pleased with that notion that you could just define this in an abstract way, and it satisfied this beautiful set of mappings and so on, and then you showed how you could multiply them, but you figured out how to do that, and so that I'm really proud of that, the differential character.
As well you should be.
Well, maybe. maybe I should be. But anyway, so that was a high point for me.
And you also, I think, were very convinced, even at the time, that this was something significant.
It was.
Yeah,
I was definitely convinced.
yeah. Although I'm sure you didn't foresee that they would become important in string theory, since no one knew about that at the time.
I think they still haven't become important enough. No, but I did tell Yang that these things existed. There were measurements in bundles with connection, and you guys, I said, you physicists are all busy with bundles with connection, and gee, maybe these things would be worth something. So, but he didn't bite.
I wonder if we could backtrack just a little bit, what your memories are of the atmosphere in the Wild and Willie early days at Stony Brook.
Well, we had a lot of money. When I got there, they were flush.
We had a lot of parties.
We had a lot of parties, but I was able to hire a lot of people was the point. So we brought in a lot of young people. 10 people the first year. I hired 10 people the second year. And we had to move some people out, as you say, who didn't have tenure. We had some great, it was a great bunch of people, and we had a lot of fun. What really made that year was getting Axe to come. Yeah. And once Axe had agreed, a lot of people could, that was the existence theorem. One could attract a great mathematician to Stony Brook. So others came, and of course you accepted as well that year.
Yes, Detlef.
And Detlef. Well, Detlef said he'd come if you came, and you said you'd come if he came, but then he said he would only come if Wolfgang came too, and so we ended up with three hires in geometry. But
well, David Eben also.
Oh, David Eben, yeah, I forgot about that. David came that year, yep. So there were 4 in geometry and analysis. Ron Douglas came, and Roger Howe. I think Roger Howe was hired. It's the best set of letters I ever saw in anybody, or at least any postdoc.
Did you know that when I was at Harvard, I was a grader for a course where he was a student?
Oh, yeah?
I noticed there seemed to be this very smart guy in the course.
Yeah.
It was the regular advanced calculus course. It wasn't the special Math 55 theoretical course.
But it was great, and the administration let me have my way, and we demonstrated good abilities to get good people, and we had a lot of fun.
So I remember one phrase in particular that you used to use at that time, and say about someone either we were trying to get or we had gotten, say, he's a real guy. Yeah. You remember that?
No.
One of the people that we were very interested, we used to talk about getting, although it never happened, was Costant, who I guess you knew going back to the time when you were a graduate student.
You know, he was my thesis advisor.
So what was that like?
Well, it was.
So he's an unusual person.
He's an unusual person, and I learned a lot from him.
What was unusual about it?
He didn't encourage me in the problem I had picked out to solve. He felt it was too hard, and my approach was wrong. And and I think if I had been
so you picked the problem. Who picked it? You picked the problem.
Well, what happened?
This was an algebraic version of the classification of holonomy groups, right, or candidates? Yeah.
Yeah, it proved, but it was a direct proof of transitivity. A direct proof of transitivity, and I algebraicized the whole thing. And, and it was.
After they were classified.
They'd all been classified. And
then it was observed they were all transitive on the unit sphere.
And I had been he'd give me some papers to read that I thought that were great. Some of his, one was a paper of Hochschild and it was two guys, Hochschild and a topologist I can't think, cohomology of Lie groups and Lie algebras, and they really sort of made all that very much come alive, and I learned a lot from that. But I was playing around, and I made a little calculation, and it seemed to lead in the direction of transitivity or non-transitivity or something like that, which I hadn't known was a problem. I didn't know the classification, and I didn't know that these were all transitive. No, I didn't know that. But I saw this calculation. I mean, I made this calculation, and I showed it to Kostant, and he said, "Oh, Hunt did something similar." I said, "Oh, yeah." And then Kostant mumbled about
Hunt? Gilbert Hunt?
Gilbert Hunt. Don't ask me why. I didn't know who Gilbert Hunt was, but he said Hunt had made a similar calculation in some paper. And he said, you know, it's conceivable this could inform the question about this transitivity. And I said, oh, yeah, well, what's that? And then he told me what the problem was. And he said, you know, it's a hard problem. He told me, Singer tried to solve it. And, I mean, he was saying, this is a hard problem. Oh, okay. But I was intrigued by it, so I just started thinking more, and I came up with a scheme. I came up with a scheme, a whole scheme, and I showed him this scheme. And he, you know, it was kind of following how you analyze Lie algebras, finding a maximal Cartan subalgebra and then looking at that as it acts. You know, you look at that under adjoint represented on the maximum, you know, abelian subalgebra, commutative subalgebra, and then it has roots and weights and all that kind of stuff. Right? You probably remember that.
I do actually.
You do.
Although
and
I never fully internalized it.
Well, I had fully internalized it at that time because I'd studied that stuff with Singer the year before, my one graduate year at MIT. So I was pretty imbued with roots and weights and that. And I thought, oh well, maybe you could follow the same general procedure, a maximal totally geodesic submanifold. Anyway, there was an analogy, and I showed him this, and he was very dubious. Mm-hmm. I just liked that approach, so I just carried on and did it. And I had communicated with Singer once. I wrote him a long letter showing what I was doing, and he wrote back very encouraging.
So you were out in California by this time, in Berkeley.
Yeah. And this was near the end of my my first year there as a graduate student. And I only spent 2. And then I made a lot of progress, and I came back to Boston in January of the second year there, and I was stuck on one point. I couldn't make something work, and Singer was nice enough to come, and it was a snowstorm. He remembers that better than I do. But anyway, we sat in his office, and I showed him how far I'd gotten, and I said, I'm stuck on this point. And he said, yeah, but you've assumed irreducibility. I said, oh, yeah. That was the end of that. I mean, he saw, I mean, somehow the whole thing was supposed to be, the manifold or the algebra, I think, was supposed to be not a product. It was supposed to be, you know, irreducible. And I had forgotten to use that, and I was trying to prove this thing, and he said, well, it follows immediately from irreducibility. So that was that was a final breakthrough, at least I thought. When I got back, I found another problem, which I solved one day in the shower. And I don't remember exactly what it was. But anyway, so Kostant was, you know, but I learned a lot of math.
What was his reaction when you did it?
I guess he was bemused, pleased. I don't know. I was a student. I suppose he was happy. I don't remember exactly what his reaction was when I did it, but it certainly wasn't a negative one.
Doesn't sound like it was all that positive either.
Well, no, I think it was positive. I think it was positive reaction. It was a long time ago, and I don't really remember. But I remember more his suggesting that this was not the best direction to go. And it may have been good advice, because I think the scheme looked a little harebrained, and he knew it was a very hard problem, and it's not necessarily so advisable to give your thesis students the hardest problem in the world, because then you're going to have them for a long time, and maybe they ain't going to finish, right? So I've never criticized him for not, being more encouraging, but I liked it. So that was my thesis, and it got published, and I went to MIT to be a Moore instructor.
So you were a Moore instructor before you came to Harvard? Is that what happened?
1 year. 1 year. Then I resigned from that because I thought I was going to go to South America and work with my friends to make this plastics business.
Right.
And I soon realized that was a big mistake. In those days, there was plenty of money around, and Bott put me on his contract at Harvard. So then I went on Bott's contract, and then they both, then I could have been an assistant professor either place, and for some reason I picked Harvard. That's how I met you.
That's right. So maybe you could talk a little bit about what Singer was like, what your relationship with Singer was like.
Well, I can't talk about Singer without talking about Ambrose first, because it was through Ambrose that I met Singer. So Ambrose was, I met him in my sophomore year, second year at college, and he was teaching analysis. And I had a terrible time with the first semester of analysis. Deltas and epsilons and point set topology and all that stuff, I couldn't make head or tail of it. I found it boring, hard, and when I took the final for that quarter, for that semester, there were a bunch of problems. I couldn't solve any of them. I really hadn't. I did, but I didn't realize it hadn't absorbed the material. And I just wrote him a note saying, I seem to be able to do other things pretty good. I was taking complex variable at the time. I was okay with that. I was doing Galois theory. I was okay with that. I wrote him this note. I said, but I haven't understood head or tail of this course. So he was nice enough to give me a D and let me go on to the next semester, which was basically differential geometry. It was Stokes' theorem, and it was integration and Stokes' theorem and that kind of stuff,
So was it differential forms?
Differential forms. He defined differential forms and proved the Stokes' theorem. I thought that was the greatest thing. I went from understanding nothing to understanding everything. And oh, by the way, the stuff that I thought I didn't understand in the first semester began to crystallize, and I understood that too, although I never warmed to it, but I did understand it. And so one day during that semester, I went to Ambrose to talk to him in his office, to ask him the following question. So I said, Professor Ambrose, when learning mathematics, is it better to learn a little bit about a lot of things or a lot about a small number of things? And he looked at me and he said, one can make the cliche either way. That was it. I said, no more. And I realized the interview was over, and I left. But I forgave him for that. That was Ambrose. But
So did you take anything away from that?
nothing whatever. Well, I took away that Ambrose was, once, some years later, I was with him in a car in Berkeley. He had come to visit, and we were driving. And we came over a hill just as the sun was rising over San Francisco. And it was very beautiful. And I said, isn't that beautiful? And he said, thank you. He was a very literal fellow. But he was very inspiring as a teacher. And then he began to work, he was working with Singer, and I would begin to see them in Jack and Marion's, the restaurant Jack and Marion's, late at night. And the two of them, I think, were working on the Holonomy theorem at this point. I learned later. They'd be sitting there, and I wondered, who is this other guy? You know, Ambrose was an old guy at that point. He was like 50. And Singer was maybe 35. He seemed, you know, senior, but, you know, not quite at his dotage. And but I thought, this is so cool. Here are these two old guys, you know. This is their job, is to sit in Jack and Marion's at 2 in the morning and do mathematics. I thought that was great. So I got to know Singer in a year or two later there at MIT, and all those roots and weights and stuff like that. So in my first year as a graduate student, my last year at MIT, I did a reading course with him on, you know, the Cartan seminar notes on Lie algebras and Lie groups. I don't know if you know those notes. Inadvertently, some years later, I saw a letter that he had written about me. And it said something like...
Inadvertently.
It was inadvertent. I don't know. It was lying around somewhere. I don't know how I saw it. I wasn't going through his files. It was just there. I don't remember the circumstance, but I remember the letter, and it said, in effect, sometimes this guy seems very dumb, but other times he has terrific insights. And I remember thinking, that's me. You know? So, but Singer was, you know, he's such an outgoing guy and helpful, and he became a very good friend.
What does he bring to the table that's made him so, made the mathematics that he's done so important and influential?
Singer is very broadly educated. He started in physics, actually, and then moved into mathematics, and he did functional analysis and C-star algebras and stuff like that.
Right. There's this, I guess it's an article by Cadison. I don't know if you know it, about his early work in function algebras, which is entitled, Which Singer Is That?
I see. Well, that was that singer. It was the same Singer. Then he got into geometry, I think, a little bit later, when he and Ambrose were working together. I don't know exactly what his trajectory was. But the important thing, I think, was that he was very broadly based. He knew a lot of mathematics from different points of view. And certainly when he got into the index theory area, when he and Atiyah, all that stuff he knew about functional analysis, I think was probably very helpful in the development of that work. So he was a broad guy, always interested in learning something new, and always interested in helping people, as far as I could see. So he's really a wonderful guy, as everybody knows.
Well, I recall on another occasion you said Singer is deep. So, you know, even after the index theorem, you had confidence that he would be doing important things.
Singer was not the fastest guy.
Yeah, very different from Atiyah, for example.
Very different from Atiyah, right. But obviously they made a great couple.
Well, Singer had other important collaborations too, I guess. I mean, Ambrose, for one.
Ambrose.
McKean and Singer.
That's right. Ray
Singer.
Ray.
I certainly know about.
Yeah, he must have had a lot of collaborators. I don't know. He was he had to be a lot of fun to work with.
Do you have any comments on sort of the joys of collaboration?
The last piece of mathematics that I did before retiring from the field was in 1977 in the summer, and I went to a conference. I was already thinking about investing and that sort of thing, and but I went to this conference in Japan, and which I had accepted a long time ago, and I'd never been to Japan, and that sounded exciting, and I had a good time there. But I had to give a talk, and it was actually pretty amusing, because I had some money by then, but I said, okay, while I'm at the conference, I'm going to, you know, be like everybody else. So I had a hotel room that was the size of like 3 telephone booths or something. I mean, it was really small. And I had to give a talk in the next day or two, and I didn't know what the hell I was going to talk about. But I'd heard about, I don't know, something to do with Yang Mills forms. Well, I can't remember with symmetries, but I do remember getting an idea and showing that there was something was unique. There was only one, there could be only one such structure. And I paced around in this little room, and the floor was littered with papers. You dropped 3 papers on the floor, it would have been littered with papers because it was so small a floor. And I came up with this result. I thought, okay, I'll talk about this. And Blaine was there, and Mary Louise. I had just met Mary Louise for the first time. And Blaine saw the talk and liked the result. And he saw how to generalize it in one thing or another. And a few months later, he said, would you mind if we wrote this paper up, and we'll put your name on it along with and I think there was a third person, I don't remember.
Probably Jean-Pierre, right?
Could have been Jean-Pierre. It could have been. But in any event, there it was, and so that was a joint paper, but really we didn't collaborate. I like collaboration. You know, when I started Renaissance, it was all collaboration, and I really like that. Just working with somebody else, and you know, sometimes it's frustrating, but when it's going, it's good. Well, you collaborate a lot, right?
Yeah, yeah, not exclusively, but a lot.
Yeah.
Yeah, I mean, I find that every collaboration is different. What do you think?
Well, you have to work with different personalities. I mean,
Right.
from
Different personalities, different strengths, different relative strengths.
from Chern to Dennis Sullivan is a big difference.
I thought at some point I would ask you what it's been like having come back to mathematics after quite a hiatus, and now working with Dennis, who's an unusual character, to say the least.
He's an unusual character. I tried to hire him at your suggestion, I think, when I first came to Stony Brook, but he didn't bite. Do you know, I learned a different way of looking at things. I mean, I've learned a lot from that. And I think he's probably learned a little something from me, because I can do some things that, but he's not necessarily so good. But but he's a masterful mathematician, and he sees things, categorically, and he's a very big picture guy.
Right, another guy who's not that fast, I would say.
That's right.
At least not that fast in a facile kind of way, although he's pretty fast to get deep insights sometimes.
Yeah, it's been quite positive. We argue a fair amount. I mean, I argue with him more than I never argued with Chern. There was nothing to argue about. I don't think.
Did we used to argue? I don't think so.
We may have argued a little bit.
A little bit, but not much. I don't
Not too much. Dennis and I argue quite a lot, and we work it out. I mean, we don't.
Dennis doesn't let anything go by, right? I mean, if he's not completely sure of something, he wants to stay right there, is my experience.
That's right. That's right. You know how it is in math. You get a feeling for what's likely to be true and what isn't likely to be true. And you get that intuition from some years of working in a certain regime and doing certain calculations or whatever it is, and and you have a feeling no sense doing this calculation. It isn't going to work, or you start it a little bit and say, no, I can see this is not going to work. I don't think Dennis is not a big calculation guy. His insights are really geometric in a sense that mine are not. I mean, he really sees things in all their...
Yeah, I would say geometric and also structural somehow.
Yeah. So he has those things, but so he'll sometimes urge me to do some calculation, and I say, it's not going to come out. It's just not. It's just... Believe me, but he has a hard time sometimes believing that. But on the other hand...
Who's right?
In that particular area, so far, I'm right.
Yeah, I mean, because I always thought of that as one of your big strengths, is both choosing which calculations to make and then being able to make them.
Yeah, I'm pretty good at that. But usually you need a good idea of how it's going to come out before you really do it. A general idea. Maybe so you can see pretty early that there's too much against this. This isn't going to happen and give you a good answer. So we argue about that, but it's great fun. I mean, he has tremendous enthusiasm, and I like writing. Actually, doing the writing once I know what I'm doing. I like to get the notation straight and to try to make it as clear. I think I'm a pretty clear writer.
In 1976, you went into business,
Basically,
and
yes.
I remember I didn't entirely approve of this decision, at least initially. But certainly one would have to say eventually it worked out very well.
Worked out.
You know, have you met people in that career who you found extremely impressive, and was it in the same way or in a different way? I mean,
That's an interesting question.
people on the same level, let's say, but possibly in a different way.
Well, once we started hiring scientists into the work, mathematicians, computer scientists, physicists, that took a while to do before we were 100%. I would say no, and I don't think in my business life, I've certainly met a number of people and have some friends, but I'm never quite as comfortable. So I don't know. I haven't been blown away.
I mean, even with the scientists.
Oh, with the scientists, some of them I have.
I've met some of them. They're very smart people, but, you know, maybe in a slightly different way.
You mean the Renaissance people? Yeah. Oh, yeah, they are smart people. Peter Brown is a very smart guy and so on. So, but I feel comfortable with those people. But I've always felt like something of an outsider, no matter what I was doing. So in mathematics, I was immersed in mathematics. I was a mathematician, but I never felt quite like, oh, I am a member of the mathematics community. Never really felt that. I always had a foot. Similarly, I certainly never felt I was a member of the business community. I feel like more of an outsider in business than I do, than I did in mathematics, even. On the other hand, I definitely liked the business that I was doing. It was great fun, very satisfying. We made money in a different way than I think than anyone had done it before.
How satisfying was that? Because in a way, I mean, it was really quite an achievement. There's so many people around the world, who are investing in the stock market, watching the stock market, all sorts of people. And in a way, the record shows that you were, at Renaissance, were the ones to crack it and say, there are these systematic phenomena that you can make money off of.
Yeah. Not just in the stock market. In fact, remember, we started in currencies and interest rate instruments and that sort of thing. It was back to doing research. I mean, at first I did it on a fundamental basis, and in fact, we made more money per hour with fundamental trading, at least certain periods, than I ever would have made with the systematic trading that it became. Gradually, I could see that the systematic stuff could have legs. So we started in currencies, interest rate instruments, commodities in general, but then started building systems, and that was the real breakthrough. If I'd stayed with fundamental trading, I would have had gotten colitis again or something. It was a big strain. You never know quite where you stand. You come in one morning, your position is way up. You say, "Oh, I'm a genius," and the next day it's down. "Oh, I'm a dope." And the reality is, you're not really a genius. You're not really a dope, and maybe you're actually going to make money on this thing. But the volatility was too high. Making models, on the other hand, if you could find some statistically significant factors, that was that was great, you know. Not only for the satisfaction of making some money, but just the thrill of finding a new predictor. And we found lots of predictors over the years. You find a new predictor, and it's really terrific. You know, you run the simulation and you see, oh my goodness, this is a real statistical advantage to this particular predictor. And it's independent of the other ones and so on, and you build up the system that way. I found that very, very gratifying. The risk control things, I mean, dumb things maybe, but nonetheless, how to model, for example, how to model costs, the right way to model costs. There was something of an intellectual content there.
Yeah, so it sounds like the words even have some similarity to, like, the right way to do minimal varieties.
Yeah, yeah, that's right. We found what I consider the right way to do this modeling, at least one aspect of it. I think we found the right way. And, well, someone can come along and do it better. I don't doubt that will happen sometime, but we were certainly a pioneer in this. And when we started it, there was nobody else doing that, as far as I could tell.
So how much of this, to come back to something I mentioned earlier, did you foresee a long time ago as a possibility, but when there was less computing power? So I can remember, for example, hearing from you about the problem of speech recognition.
Yeah.
And it was supposed to be so hard, but, you know, now...
Still hard.
Still hard, but it's something, right?
That's right. That's right.
So I'm just curious as to whether you were able to dream ahead. Gee, if we had, you know, computers that were 1,000,000 times faster, we could do something like this, or was it a kind of gradual evolution?
I think it was more of a gradual evolution. The computers were always adequate to do what we thought would be useful at the time. As we get into faster trading and analyzing more data, but you see that all that came because computers have gotten better. So there's more data available because there's more bandwidth available, there's more storage available, not just in our office, but all over the world. So more and more data gets generated, computers get faster, we learn to use that additional data, and so on. So it's, I don't ever recall sitting back dreaming of what we could really do if we had a quantum computer. I don't know what the hell we'd do if we had a quantum computer. But by the time we actually had one, we'd probably have figured it out. You know, so it's kind of scary. I mean, I remember being at IDA, and they were going to get a new machine. It was going to be the biggest machine in the world, and it was going to have 1,000,000 words of storage. Now, a word was 60 bits, so it would, you know, it was like 8 million bytes of storage, whatever, right? I mean, 8 million bytes of storage is nothing. Nothing. This was coming, and we didn't know how we're going to use all this storage, right? It turned out within 3 weeks it was absorbed, but I didn't know. What are we going to do with 1,000,000 words of storage? It's an awful lot of storage. Core, it was called core memory at that time. So maybe I've never had enough imagination to think about how you'd use, you know, infinitely fast computers.
enormous amounts of data and exist now, and people are trying to look for ways to process them and extract predictions from them in all sorts of fields. So I wonder if you have any thoughts about maybe how dominant, is this a real paradigm shift? How dominant will it become? Will it really change our lives? What role, if any, should math departments play in this? This is something that I have to wrestle with right at the moment in the next coming years.
Well, I don't know what role math departments should play in it, but I do know that there is more and more data coming out and more data to analyze, and more. I learned words that I didn't know. There was a megabyte. I got, okay, a megabyte, then a gigabyte, okay, then a terabyte. I thought, well, that's pretty much. Now it's a petabyte, which is 1,000 terabytes. I can't remember how many zeros all these things have, although we could figure it out. But so here's something I learned just the other day. So at Cold Spring Harbor Laboratories, where they do biological research, and we support some of that stuff, they need petabytes of memory. What?
No kidding.
God's name can they do with petabytes of memory? Well, it turns out the following. So you really want to understand. See, our brain has like 1 trillion cells or more. I mean, our brain has, and all of those have dendrites, and they make connections to each other and synapses. It's a huge amount of information. It's in a brain, even in a mouse's brain. So I'm going to get to a mouse's brain. So you take a mouse, you sacrifice this mouse on the altar of science, cut off its head, freeze it, and begin to slice the brain. Now, you can slice its brain, this latest incarnation, at 10 micron slices, and each slice will have resolution at a micron. So you'll get a tremendous, okay, so these dots are every micron in this square array, this rectangular array, you have a dot. And now every 10 microns, you have another slice. And you add all that up, and it turns out it's a hell of a lot. Now, what do they want that for? Because they want to really understand networks. They really want to understand structures, very delicate structures. And this is big stuff. So, and not only that, it's not one mouse. It's 1,000 mice are sacrificing themselves on this altar. So now I got 1,000 of these things, and I want to compare them and make sure everything is lined up. So, because there's a statistical difference, you might not know this, but not all mice have exactly the same brain. So there's little differences with mice. And so here's an example of research that it's going to be good research. We're going to learn a lot more than we know, but it's going to just require a huge amount of data and computer processing. So I don't know what math departments ought to do about that, but kids need to learn, get comfortable with statistics in one thing or another at some point in their lives.
I wanted to come back a little bit to this period around 1976 when you finally decided you were going to not be a professor anymore and go more or less full-time into business. So yeah, how did that decision come about, and what was in your mind when you were making it?
Well, it came about because that business in South America that I alluded to from '62, and when I came back to MIT to teach, and I immediately started, for some reason, started thinking about my friends in South America and how they should do a business, and somehow we should invest in it, although I didn't really have any money. And I did go down there and get them going, sort of just spiritually rather than anything. But 12 years later, in 74 or 75, maybe 74, they sold a piece of it, and there was some capital, and that capital was largely was my family's, but our mutual friend Charlie Freifeld invested that, and it did pretty well. And so then I had, anyway, the family had some money. And so I felt two things. One, that money was enough to keep me going for a while. And I found this whole process of speculation and quite interesting. In particular, I'd gotten interested in currencies. So I figured I have a little money. There's something else I'm interested in. I was, as you may recall, very frustrated with the work we were trying to do.
I recall that very well.
You remember that very well. Proof some numbers were irrational, which is still not known. But that was supposed to be the punchline of our paper, and on these differential characters and so on. And
although we did get the application without proving they were irrational, the application we had in mind.
How so? I don't really...
By using these automorphisms in these examples. They weren't continuous automorphisms, but automorphisms nonetheless. So you could drag you could bring the real classes in and drag them around.
That's right. That's right. So we found some rank in the that discretized Lie group of the homology, but nonetheless, there was bigger game there, and we weren't able to really get it, and I was frustrated. I was between wives, and had this new opportunity. So it seemed perfectly natural to just do it. Chern told me a few years later, he said, a lot of people said, oh, it's a shame Simons is leaving mathematics and so on, and he said, as I think I've told you, he said, well, yes, but after all, he wasn't David Hilbert, or something to that effect. And he needn't have reached that high, but he made the point that somehow the subject would limp along without me, and as of course it has. So I was very excited about this new.
Yeah. See, I felt during those first years that you were really losing something because you weren't hanging around all the time with mathematicians anymore. So from my personal perspective, I thought this was a step down.
Yeah. Marilyn, on the other hand, my wife, thought it was a step up. At last, she could hang around with people and she'd know what they were talking about. I liked being around mathematicians, and that was fine, but I was having fun with new people and just having fun exploring this completely new regime for me, speculation. And the currencies, which I found interesting, had just gone off of fixed exchange rates, which they had until the middle 70s. So you couldn't speculate in currencies because they didn't go anywhere. So they were free to trade, and the prices were moving around, and I had some ideas on where they'd go and so on, and so it was fun and successful. So I never really looked back. There was never a time when I looked back and said, "Oh, I miss all that mathematics." It was just a new leaf in the book. It wasn't that from time to time I wouldn't think about it.
Yeah, I know that.
You know, and I would think about it from time to time, maybe do some kind of a calculation, but I was mostly always pulled back into the business. And so for almost 30 years, until 2004, I was out of it. Didn't do any mathematics. And then I got back in 2004. and have been sort of a mathematician again. I mean, you don't stop being a mathematician. You know, someone asked me a couple of days ago, so they were asking me something, and I explained about it. I said, how do you remember all that stuff? I said, well, you just don't forget it. I mean, I didn't forget anything. As I also said, such a giant store of knowledge I didn't have because I was not the most broadly educated.
You didn't have all that much to
That
forget.
much to forget, exactly. But I had something to forget. But I didn't forget anything.
Based on intermittent phone calls that I would sometimes get, that you, for one thing, continued to think about the same problems we were stuck on.
Yeah.
Right. And
I did.
the amazing thing is 30 years later, in this work with Dennis, you actually kind of solved them.
Yeah.
At least some of them, not the irrational number.
The irrational number.
So when you started working more actively, so I know first you had some ideas that you came to me with, and I pointed you in the direction of Dennis. I thought he was really the person with whom to discuss these things. So how did that happen?
Well, that was in the winter. Really, the winter of 2003, the spring of 2004, and what had happened was we had a tragedy in our life. We lost our son, and Nicholas, and that put me in a very contemplative mood or mode. And we were spending some time down in Florida. We had taken a house down there for the winter, so we'd have a place to go weekends because we just didn't want to hang around the house and mope. So we rented a house in Palm Beach, and we'd go down there, not only for weekends, but we'd spend a week or two at a time. And I remember sitting outside in the back patio, and I started thinking about mathematics again. This question of uniqueness of differential characters, whether the diagram completely characterized the thing. And I just started working on it, and I found mathematics was sort of a wonderful place to be, because when you're doing that, you're just not thinking about anything else except the problem, and it was like going into a cocoon of some sort. So, and in fact, I was getting somewhere in that problem. I could see some easy facts that were leading me to think that one could prove uniqueness. And then I came to you, and we fooled around with it some, and then I was in Nepal, again in connection with Nick, to set up something in his memory, and thinking about the problem. And we had looked at it that what you want to do is map the space into something and pull back into a place where the diagram or what did uniquely characterize the thing, and then you pull it back and so on. Some functorial argument like that. But while sitting on the steps or the balcony in this hotel, I started thinking, wait a minute, it's not you want to map it into something, you want to map something into it. And I could see how this would work just fine as long as you could realize every homology group by a manifold that was mapped in. The image of its fundamental class would represent all homology, and then I saw quickly how you would prove it there. And then I came back to you and said, is every homology class represented by a manifold? I think I came back to you and said that. Yeah. It was funny because very shortly thereafter, Dennis had come to see me to ask me some advice on something or other. I don't know what, personal advice on something to do with his kids. I don't remember what it was exactly, but he walked into my office and I said, aha, the very man I want to see. And I asked,
Oh, I actually feel quite proud of having gotten you two guys
yeah,
together.
you got us together, and I asked him this question, and he likes to tell the story. He said, "My boy, sit down." I'm going to tell you the version. The answer is no, but it's almost true, and so on and so forth. Immediately, since a multiple of it, of any class, could be realized by a manifold, we could see that, okay, the R mod Q uniqueness was there, because then you could just do the thing, and it didn't matter if it was a multiple. You're just going to divide by something. And so I said, okay, but now that's great. And I said, is there such another theorem? And he said, yes. And I said, is there such another theorem? He said, oh, no, that's hard. That's hard. So then he started thinking about it. And then he brought in pseudo-manifolds, something I'd never heard of, and pseudo-manifolds.
Yes, I know them well.
I'm sure you do. And so did he. And he showed gradually, put the pieces together, and how one could really do this theorem using pseudo-manifolds as the representative. So I was extremely pleased with that. And then the uniqueness on the multiplication. Again, I saw some algebraic facts that should lead to that. It sort of made a preposterous. If there were two different ones, you'd have some topological invariant, which would, whoever heard of such an invariant, and then he, through some legerdemain, said, yes, it can't exist, so the multiplication is unique. So the whole thing came out. And so that's what got me going. But right at the beginning of this, he was saying, okay, well, fine, but we have to do this for K-theory instead of ordinary homology, cohomology. And
but you had always had this dream about K-theory with connection.
I had. But the
For
thing
bundles
is
with connection.
that his proposal was different. His proposal was you make characters in the same way, and he had a slightly elaborate way of making characters, which turns out in the end to be a perfectly good way of making characters, and that's what we're fussing around with now. But as we went through what you needed to prove this and so on, or to construct this thing, and then these things, what it really looked more and more like was what you just needed was bundles with connection with a certain equivalence class on those connections. And so I instead of fussing with the cycles, I said, what about just this? And so that turned out to be a very good representative of the differential cohomology. And there was one slightly tricky part of it, and even there, one result that you and I had in the famous Stanford notes about the direct sum, and when the direct sum of two connections was equivalent to the in a certain sense. We weren't saying it quite that way. We were looking to make inverses. It turned out that was a very useful approach to show that every vector bundle had an inverse, and so on, with connection had an inverse. I got back into it, and sometimes it's good, sometimes it isn't so good. But
What, doing math again?
yeah, on the whole, it's good.
Sometimes it's frustrating, or what?
Yes. Sometimes it's frustrating.
You think this applies only to you, or what?
No, I know,
You think
I
you're
know. But I'm,
something special?
No, it's not the only thing I'm doing. I'm juggling all these different activities at the moment. But
You're supposed to be retired.
I'm supposed to be retired, that's right, but I ain't.
So what do you have to say about this latest phase? So which of course includes the foundation and all the support for science. So
It includes a lot of things. I'm involved in a lot of things. But it was not, as it turned out, a joyous transition. So going from math to, even going from math to academics to IDA was a smooth and fun. Going from IDA to being a chairman was smooth and fun. Going from chairman to going into business and leaving that was smooth and fun. This has been smooth, but not as much fun as I thought it might be, because ever since I was the chairman, since I was 30, I was a leader of something. I had a group of people around me. We were working together, but I had, a leadership role. And I really like having a leadership role. And so I ran my company for many years. I was the head guy. And I finally decided that it was a time to turn it over to the younger people. I was 72. And my daughter Audrey was about to graduate college in the city, and that would make us, Audrey, she had some special needs, and so we didn't want to do too much traveling without her and so on. And she graduated, and I retired. And now I have to try to figure out how to live in this new estate where, yes, we have the foundation, but it's an enterprise that funds others rather than sort of organizing a bunch of guys and let's solve this problem. We're paying other people to solve problems.
But still, I mean, you're involved, as I understand it, with evaluating the proposals,
Sure.
and you're, I'm sure, deciding what it is you should be supporting.
Well, even that, to some extent, yes, but when you're giving out individual grants, let's say for research in neuroscience, in which I'm not an expert, I don't have any say, and I don't want to have any say in how those grants get given out. Sometimes if it's a very big one, they'll come to me, or we'll say, well, maybe we should cut this back a little bit or whatever. But basically, I'm not in a position to make those judgments. Now, for certain other grants, I am. And I work with Marilyn, my wife, but it's still a kind of a working with gloves on, if you know what I'm saying. I'm not sitting down with a pencil, doing something very concrete, or even suggesting some new predictor. Let's get the guys together and talk about the possibility of this or that. I'm not really doing that. I have responsibilities at the university. I'm trying to help Stony Brook get on its feet. I have a battery company that I'm trying to make sure succeeds. Math for America, which we might talk about, is an organization I got started about 7 years ago, and I want to see that succeed. But in every case, there's someone else who's doing the work, and I am watching over them. You might say, well, that's being a leader, right? But not quite, because they have so much autonomy, intentionally so, that it's not like I'm interacting, every couple of days and say, maybe we should tilt it this way, maybe we should tilt it that way. So it's
Certainly understand what you're saying, but
yeah.
I mean, on the other hand, couldn't you argue that, which is neither here nor there, that you have so much more scope now in this way? I mean, you can really sort of influence the way basic science develops in the country.
I can.
And you are.
And we are, and that's all fine. And I enjoy that, but there's still a hollow spot that needs to get filled, and it will. I mean, well, I will adjust to this.
So just doing math at this point doesn't fill it?
When the math is really going good, by the way, it does. Because then, like this morning, if we hadn't been this interview, there was a calculation I really wanted to make as soon as I got up.
Don't look at me, it wasn't my idea.
Here we are. But I discovered something yesterday that I think is very interesting. I think it's interesting. It probably won't be, but I think it's interesting. And this came out of a discussion with Blaine Lawson.
Oh, no kidding.
Because I wanted to look at the Dirac operator, but when the connection in the tangent bundle was preserved the Riemannian structure, but it was not the Riemannian connection. It was some other connection in the tangent bundle preserving that. And you can write down a Dirac operator, and I wondered if that would satisfy the Atiyah-Singer-Patodi theorem, that version of the Dirac operator, when you did it with respect to a connection that was not the Riemannian connection, but it did preserve the inner product. And over the phone, he said he thought that would work out okay, and we started to do the calculation, and then he said, oh, we got to show it's symmetric. And it turns out it's not symmetric in general. On the other hand, there is a class of connections for which it is symmetric.
For which is symmetric?
For the Dirac operator, yeah. There's a class of connections for which this operator is symmetric. And it has to do with, there's obviously torsion, because otherwise it would be the Riemannian connection, because this is connections which already preserve the metric. So there's a property of torsion that if the torsion satisfies a certain property,
then the Dirac operator
then the Dirac operator is symmetric. I think it's a torsion. It's a symmetry.
must be.
It can't be anything else, right? Because the torsion, the difference in... Anyway, so I was excited to try to make this precise, see just what it was, and start learning about this family of connections. So I was very pleased.
Very Jim-like, a very Jim-like enterprise.
Yeah. Well, there it was. So when I was doing that, but then I had to give an interview. I have a meeting. So all day long, I'm not going to be able to make that calculation. And probably by tonight, I'll be too sleepy, but I will get it done. So yes, when it's going good, it definitely fills every void.
So is that the only possibility, or could the other activities, be augmented in some way that you would have more hands-on involvement?
We're thinking hard about that. I'm thinking hard about that. We're also thinking hard about how the direction of the foundation. The foundation is growing. We're bringing more capital into it. What's its ultimate or disposition? Direction. Let me put it that
Yeah,
way.
that was one of the things I had in mind to ask you about, actually.
Yeah. Well, it's a good question. You can ask me right now.
Okay, consider yourself asked.
Well, it's a sizable foundation. It's going to get a fair amount more sizable. And, what should we do that's different, and of high quality? But how should we organize it so I and Marilyn get the most pleasure out of this, and yet we're not just another foundation, giving away money for worthwhile things somehow.
Yeah. Well, I mean, already you're not that, I would say.
Well, already we have our own cast, and that's good. But it's, I'd like to bring some more work actually in-house. Is that a possibility? Can we bring some research in-house? Can we move almost in the direction of a research institute, where, yes, we'll support outside research at other places, but we'll also build an internal component along that? What kind of research, what kind of project should we focus on? Right now we have a big autism project. That's very exciting, very focused. Other things are a little more pedestrian. So the future of the foundation, I think, will occupy me, and perhaps begin to fill that sort of hollow spot that still exists. So, it's a feeling of irrelevance. I was telling Marilyn, I said, I feel irrelevant. She said, what do you mean you're irrelevant? You do this. Yeah, but I'd still feel irrelevant. So.
Well, it's, as Dennis once said in a related context, different, but maybe some analogy is carrying things out maybe to enough decimal points. So when my father retired, he got very depressed.
Your father?
Yeah. So he had 100 men under him in his job. So he was the chief engineer at a big engineering firm. They did a lot of work in the state. And, I think basically it was a difficult adjustment. And he didn't have a foundation to go to. And,
right.
He said he felt useless now.
Right.
Now you have all this stuff that you're doing. And still, somehow, it's interesting, there's some void there that you feel.
Exactly.
This doesn't bode well for the rest of us. I guess,
yeah.
those who might consider retiring.
But on the other hand, you see in mathematics, you don't ever have to retire. I mean, you can just keep doing
Just
it.
keep knocking your head against the wall
Right.
until you drop dead. I wanted to actually get into, science education, what it means to the country, and this is, why it's important. And this is obviously an aspect of it that you think is important.
Yeah.
So maybe you could talk about Math for America. What are the ideas behind it and how it's working and so on, and where you hope it will go.
The idea is that the country is facing a big challenge, and I think it doesn't really understand the depth and even the breadth of that challenge. Quantitative methods are more and more pervading the economy, whether it's a new computer or a new gene. The techniques required to work in such an economy are more and more dependent on quantitative methods. At the same time, the fact that that's the case means that people who are good at that stuff, fewer and fewer of them will want to teach. Why? Because they can make so much more. It's not only more money, but more respect and everything to do something else. When I was a kid, if you really liked mathematics and you were pretty good at it, you could become an engineer, I suppose, or an accountant. But there weren't a million jobs that there were no computers, which is mathematicized everything. So teaching high school math was a nice job for a lot of people. You liked kids, you had your summers off, and you could be doing mathematics.
Yeah. I know that you've made this point in particular as it pertains to women.
It's also true for women.
Particularly true, right?
Yes, although it turns out that the statistics show that the wage compression has been an even more important factor. But a lot of women had no choice whatsoever if they liked math and wanted to do something in math as a career. I'm not talking about doing a big-time researcher, but just, you like math. So a woman could have been a bookkeeper or a teacher. They couldn't even be engineers in those days. Women were verboten from the engineering business. So a lot of smart women were teaching math. So we had pretty good people teaching mathematics. I certainly had some good, knowledgeable teachers when I was going to high school. I also had the football coach who wasn't so knowledgeable, but he was just one example. The others were pretty good examples. So I had great teachers. But we're competing with the whole world here, and we're losing this competition because we're not training our people properly. So the last time we were challenged was with Sputnik. 1957, Sputnik went up, and all of a sudden everyone was afraid the Russians will next be on the moon, throwing Molotov cocktails at us or whatever it was, and there was a tremendous rush to improve and to compete in this race. And it was perceived quite correctly that our store of scientists was too low, and we didn't have our best universities didn't have big enough departments in math and physics, perhaps, or electrical engineering. And so there was a big push at a national level to address this issue. And my year, I got a PhD in 1961. It was something of the order of 100 people got PhDs in mathematics that year in the United States. Now, 10 years later, it was 1,400. And that increase was largely due to this huge effort that the federal government put in promoting people.
Of course, I remember this very well.
You do. The National Science Foundation was being built up, and the National Defense Education Act was created. And as probably you know, or possibly you know, I was a beneficiary of a National Education Act, And when I went out to Berkeley, it was the first year of it, and I had a fellowship, one of these very lucrative fellowships, and I was going to go to Berkeley anyway. But nonetheless, this was a very generous fellowship, relieved me of the usual teaching responsibilities that almost completely that a teaching assistant would have to do. And and I was the first person in the United States to get his degree under the National Defense Education Act for some reason or other. And I got a nice letter from Abraham Ribicoff, who was the secretary of HEW and so on. It was because I'd already had a year of graduate school, and I finished 2 years later, so I got my degree. So I always had a soft spot in my heart for that program. It was a great program, and it was created in the face of a threat. Now I look around, and 10, 15 years ago I started looking around and say, well, we have a threat now. It's not military, it's economic. And it's not one country, it's every country. You know, it's every country. They're all trying to eat our lunch, eat each other's lunch, because, and these other countries are preparing themselves for this by teaching their kids properly.
So what went wrong here, actually?
I don't know what went wrong. Most people don't really see there's a problem. It's easy to see when there's a problem when there's this little basketball, you know, orbiting around your head, and someone points out, there it goes again, and holy shit, you know, what are we going to do about that? But we don't have that. It's just this sort of malaise. So, well, you know, we bring in these smart Chinese kids on H-1 visas, and that's okay, and so on and so forth. And, oh, most people think their schools are pretty good. I'm not talking about the disadvantaged kids who have a special set of problems. But the average American family, I've been told time and time again, thinks their school district is pretty good, their kids are getting a good education. Now, they're not, because fewer and fewer, let's say, of the mathematics teachers in high school actually know mathematics, a minor problem. You know, they don't really know the subject, or they don't know it well enough to be teaching to the high school kids. Now, the parents can't tell that. They don't know. I mean, the kid comes home and says, Jim, I don't think my teacher knows quadratic equations exactly. She seems to be having a problem. Mother says, come on. Who are you kidding? I mean, look, that's very hard. That stuff is very hard. You know it's hard. I can't help you, but I'm sure your teacher knows how to solve it. You just have to study harder. How could the parent, if the kid's teacher can't read or doesn't read well, the parent can convince him, my God, she can't read. This is terrible. I'm complaining. But you know, she doesn't know, minus b plus or minus the square root of whatever it is, a squared minus 2ab. Gee, you know, we've got to do something about that. So, or b squared minus 4ac, as a matter of fact. Okay.
I didn't want to say anything.
You didn't want to say anything, yeah. B
Square root.
Minus 4ac. Square root, I said square root. I threw in the plus or minus, I got the square root.
2a.
But all over 2a, yes. Our students in high school, not by 8th grade, we compare in a median to our competitor countries, but by 12th grade, we're right at the bottom. So people see the statistics, oh, well, you know, maybe we need smaller class size, maybe we need computers in the classroom, maybe we need a better curriculum. But it hasn't completely dawned on people that what we need are teachers who know the subject. And a teacher who knows the subject can make up for a large class size, you can make up for no computers in the classroom, I think, you know, can make up for a lot of things.
Do you think it would be enough to fix the problem,
Yeah.
or are there also societal problems?
No, I don't know. I think if there are, well, what kind of societal problems?
You could make science and math seem more glamorous, for example.
For sure.
By inviting, you know, people to the White House, let's say, who had gotten some distinction, not just championship sports teams. You know, it would cost nothing. You know, some way to make it seem more exciting and glamorous is one example. I'm sure that the quality of the teachers is a very important thing, and it's something that you could address in a focused way, as Math for America is doing. But, you know, you wonder, is it enough?
You could make math and science more glamorous. There are various facets to the problem, and I can't say that more knowledgeable and inspiring teachers in the classroom will solve the whole problem. But it will go a very long way towards solving the problem, and hopefully other things can change at the same time. But I felt this should be a national program. We should take it with the same seriousness that we took the NDEA, National Defense Education Act, and create a program. And when my friend Chuck Schumer became senator, I assisted in his campaign, and he was grateful. And I went down to Washington as soon as he was inaugurated, or went in, not inaugurated, whatever you do when you're a senator. And I said, okay, here's my program. We got to do this. We got this big problem. He says, oh, that's a wonderful idea. And nothing happened. And nothing, whatever happened. It was one of many wonderful ideas. He'd probably heard that hour. Well, everyone comes with their wonderful idea. So after batting around and talking to people and so on, after a couple of years, we got the idea. Let's just do it ourselves as a pilot here in New York, make it good, maybe start some branches in other cities, and then with the proof of concept, get the government to make a program. And that's the course that we're on. And it's slow going, but it's not.
So where are you on that course exactly?
Well, we're on a course to make New York considerably bigger over the next few years. We're aiming for
With government participation?
No, that would just do privately. Maybe if the government comes along, it would be great. But I think
I understood that at some point they had approved something. No, but they didn't fund it, or what was it?
No, they funded it. They got a little program passed, but most of the money was wasted. And it wasn't a program exactly along the lines that it was so general that people could interpret it all kinds of ways. So little things got started in different places. Some of our programs got money from that bill, but it was a modest bill and not really well focused and buried. Almost all of the money we spend at the federal level on education is spent on the disadvantaged. It's spent on getting the ship righted. It's listing. The poorer kids are not learning as well as the wealthy kids. Let's help the poorer kids. Almost all that money. But in the meantime, we may get the ship level, but it's sinking. I mean, there's more than one dimension to this problem. It's going down, and we're busy getting it level. Of course, I think it's important to get it level. It's important to help the disadvantaged. But the Department of Education has a $65 billion budget. And the amount that's put into something like Math for America or National Teacher Corps is zero, close to it.
And how much, I'm just curious.
$2 billion.
$2 billion?
$2 billion a year to have 20% of the math and science teachers in the United States enlisted in a math science teaching corps. And that would be quite transformational, because they would inspire the other teachers, they would inspire school districts to get more such people. And you have to pay people more, and you have to make the job better in terms of respect. So it turns out it does not take a fortune. You don't have to make them as rich as they would if they worked for Google, but you have to pay them more and make them feel they're part of something that's relevant and exciting. And they'll inspire the kids. And just like I was inspired by Walter Taylor with plain geometry in the 10th grade. He was inspiring. And he knew the subject. So that's what we're doing. It's slow going, but we're making progress.
I think that it's frustrating at every level, not just this level, because mathematics is so fundamental, and it doesn't require big laboratories.
Right. Right.
It's in a way such a bargain, and yet it's hard to get it funded at what I would consider an appropriate level.
Yeah. Well, everyone thinks his own. I'm sure you could get historians to talk about their field and how it's a pity that people don't know enough history, and we all should know history, and I'm sure we should. But we don't have a shortage of historians in the workplace. When we bring in people on H-1 visas, it's not because we need people with history degrees. It's because we need people with computer science degrees and that sort of thing. So we have a real shortage here, and I agree. It's not a big trick.
tell us a little more specifically about how Math for America works?
Sure.
What are the details of the program?
Well, it's addressing two issues, recruiting people into the field and retaining them once they're there. So you could put upfront inducements to get someone to take a job. But once that's gone, they're not going to stay in the job unless it's a good one. So you could say, okay, we're going to give you a scholarship to train in high school to be in college to be a math teacher. And isn't that great? And you get a scholarship, but you have to teach for 3 years. Oh, hey, fine. So they're trained, yes, I'm a math teacher. Then they go in, after 3 years, they say, this job stinks. It doesn't pay very much. I have to deal with an argumentative principal, or whatever it is. Teaching is hard, as it turns out, in particular in your early years. There's a very rapid fall-off rate, turnover, in particular among math and science teachers. They come in and they go out. So it's not merely inducing people to come in. It's making the job good enough so that they stay in. So how does it work? People who are entering the field, we advertise, we approach them, we give them, if they're interested, we give them a test, and then we interview them, and if they look like they'd be suitable for the classroom and know math, we give them a math test. It's called the Praxis exam. It's not perfect, but it's pretty good. If they pass that, they come into the core. What do they get? They get a fellowship for the first year, $30,000, which is pretty much what a graduate fellowship is these days, $30,000. And we pay their tuition in an intense 15-month course, because they don't have teaching. They didn't study education. They only studied math or physics or whatever. They prepared them for these things. They go in for 15 months to an intense course. They learn the ed stuff that they're supposed to learn to get a master's degree.
Are they also learning math stuff?
Yeah, they learn some math.
Or you only take people who are at an appropriate level?
No, well, we encourage them to take more math, and they do.
They do. That's part of it.
Then they have to teach for 4 years, and they get stipends, say averaging $16,000, $17,000 a year on top of their pay. So that makes the first part of the job good and so on, but then how do you keep them there? Well, then there's a master teacher corps, and that's for people who already are teachers, and say for 4 or 5 years, and who've demonstrated good teaching skills and can also pass the test. We bring in those teachers either from the ranks of teachers who happen to be distinguished in that respect, and there are some, or the fellows then transition to that if they have done well in their first 4 years of teaching. So there's 2 entry points. You can be an existing teacher with a number of years under your belt, take the test. If you pass it, you become a member of this elite corps. You get an extra $15,000 a year. It's a very successful program. People love it. The only problem is, can you find enough teachers who are already in the ranks who really know the field to keep them? And the answer is no. But those people serve as examples. They serve as inducement to someone entering the field. Oh yeah, well maybe I could be a master teacher if I could carry on. So, and the master teachers help mentor the fellows, help mentor the more junior teachers. So that's basically how it works. And there's a team, or not a team, but there's advising that goes on during the person's first couple of years in teaching for the fellows. And we have events, we have dinners. In this building, people come in for seminars and things like that, almost bonding situations. So they feel great. They feel great about being teachers, and they feel great about being a member of this teacher corps here in New York. And so we'll build that up and use as an example. But we think that's about the right way to do it.
And so the commitment is ongoing.
Ongoing.
I guess, as long as they're
ongoing.
doing this, they get the supplement.
They get the supplement and become members of this corps. And what I'd like to have, as I said, is about 20%. If we had 20% of the teachers of math and science in New York City, it would be about 2,000. About 2,000.
And what percent is it now?
Right now, there's only 350 in the corps, but we're going to build it up to 1,000 over the next 4 years. So 350 here in New York.
And what do the other teachers think about these teachers?
They're perfectly happy.
They're happy.
Yeah.
Do any of them want to go back and get the further training and attempt to join it, or is it more bringing new talent in?
No, you mean
Yeah, existing teachers. Do they see this as a
well,
way,
that's how
for example?
most of our master teachers are coming from existing
From
teachers.
existing teachers.
Yeah. And an existing teacher could say, take the exam, fail it, and say, gee, you know, I need to learn some more math. One way or another, learn it, take some courses or whatever, and try the exam again. And if he or she has learned enough, well, they pass the interview process, which is fairly rigorous and good recommendations, they could join. So far, it's going very well. Will we run out of people who are already in positions to make the members of the course? Surely. That's why we need to keep bringing in new folks.
And the unions haven't resisted.
The unions don't care because
Something on top.
it's something on top. Their bosses aren't paying. It's not coming out of the school district's money, and so someone's gotten an award from God. Well, how can we complain about it? So the unions are okay with it.
Is it getting enough positive publicity?
No. I would say no. That's one of the things we've got to work on. Getting it more publicity, but it's getting pretty well known here in New York. But it definitely needs publicity. It bothers me so to see something that is so obvious not done. We had a financial collapse in 2008. Here's another example. You know, everyone's been running around like chickens with their heads cut off. Where did we go wrong? What were the problems? Blah, blah, blah. How did all this happen? We have to punish the hedge funds. We have to punish the banks. We have to do this. We have to do that. It was all outrageous. We all got swindled. Maybe. But the real problem was that the rating agencies put the wrong ratings on the bonds. They put wrong ratings on the bonds, then people would buy the bonds. People would buy the bonds, people would create the mortgages of which these bonds these instruments were created. So the whole chain just worked its way up because there was no policeman in the street. So if all the police leave New York City, there'd be a big crime wave. Then everyone would say, those criminals, they're terrible, let's punish the criminals. Well, we've always punished the criminals, but the best thing is to have some police that keep them from being criminals in the first place, right? Well, the police took a holiday. Is anything happening to the rating agencies? Is there any reform being made in the rating agencies to make sure this won't happen again? No, or very little. Why not? It's not politically interesting. It's not interesting to the newspapers. They never even heard of a rating agency. The average person would go right to sleep if they heard the rating agencies aren't doing their job. But you hear the big bankers are getting big bucks. That attracts the news or the politicians. So the key problem that created this mess is not being addressed. And when I see that, it's just very aggravating. You know, and I talk to people and they say, yes, that you're right, it is, we should do something. But they're not doing anything. Some people think teaching is a calling, and that the idea that teachers have to get paid, of special subjects have to get paid a whole lot more, is grating. Some people think, wow, Miss Jones was a perfectly good teacher years ago, and Miss Jones did, how come all of a sudden we got to pay the teachers more? Okay. Sort of a reasonable thing to say, except times have changed, and these folks are in demand. And the unions want only flat salaries. They do not want any difference between a history teacher, an English teacher, a gym teacher, or a math teacher. So they're ignoring the law of supply and demand. So you get used to certain things. The unions are used to a flat thing. People are used to teachers are humble folks who don't get paid too much. And I'm not talking about college, professors, guys like you, but, your average teacher. So people have it in their mind. Now, We know that doctors get paid a lot. We've come to accept that. They didn't always, I guess. But, you know, it's expensive to train, blah, blah, blah. So,
Though interestingly now even doctors are complaining that the insurance costs are so high.
well, that's another matter, and it's absolutely true. But, so we can't right every wrong. That's the tort lawyers are opposed to limits on these payments, so the insurance companies have to charge a lot, and everybody suffers. So that's a wrong needing righting. But you know, you have to look around and say, okay, there's a lot of wrongs. Is there some that I could do something about? I can't do anything about that. There's a chemistry, lithium sulfur chemistry. These two elements are very reactive, and when they react with each other, create a tremendous amount of energy per unit weight. So if one wants batteries as we need, that are light for automobiles, but don't weigh, you know, like a lead acid battery, you can schlep them around, but they're so heavy you can't do anything. And the lithium ion batteries are still not light enough. They don't compare to the energy density of gasoline.
So I think you explained to me one point is getting the energy out quickly for acceleration.
Well, you want to get it out quickly, but the biggest, okay, so 17 years ago, some technology came out of Brookhaven Labs to make lithium sulfur batteries, and they formed the company, and we backed that company. And for 17 years, we have been trying to make these batteries practical. And the main objection to its practicality is the very nature of this intense reaction destroys its own container. So it's like having a gorilla on the football field. Boy, he's wonderful, right? He can tackle 3 guys at once and so on. But on the other hand, you got to teach him the rules. If he doesn't follow the rules, it's no good. He'll run off and hit people in the stadium. No, you got to stay on the field. Oh, you know. So it's like that. So we got a gorilla in a can, and we got to tame him, and that means protecting all of the innards of these batteries against this fierce chemical reaction, which, when it's under control, is doing a wonderful job. And we're pretty much there. We have a nice grant from the Energy Department. We're about to become partners with a big German chemical company, and we're hoping that within about 4 or 5 years, these batteries have enough specific energy so they can nicely compete with gasoline. And so, and they're cheap to build, and yes, they have a reasonably fast discharge rate, so that's not an issue. Just have to learn to build them so that they don't eat themselves up. Eating themselves up doesn't mean causing an explosion. It just means you don't get as many recharge cycles. Every time you recharge a battery, a little of it is hurt. That's why you only get so many recharges. But we're only getting 50 or 75, and we need several hundred recharges before it's really practical. I'm really interested in electric cars. I love the whole idea. I mean, I could go on this subject. Do you realize that 70% of the petroleum produced in the world is for transport? It's for cars.
I can accept that.
It's not a majority of the energy consumed, but it's 70% of the petroleum. So now, if you have electric cars, you're going to way cut down the amount of petroleum needed. You may boost up needs for coal to generate the electricity. That's another matter, but presumably we can find a way to deal with that. But if you're only using half as much oil, if the world is, all these problems in the Middle East are going to kind of go away. I mean, there won't be our problems anymore. Maybe they'll be their problems.
It's a nice thought.
It's a great thought. I mean, imagine if oil consumption was just cut in half. We'd be able to produce our own. We wouldn't really need to import. It would be fantastic. So I love electric cars. So hopefully, that's our battery business. 17 years I've been at it. And we're doing a deal, I think, with this German company. And we looked out at royalty schedules, and so we said, okay, this was just yesterday. All right, if we do this deal, all royalties are going to end in 2032. It was going to be 2030. I said, 2030, I'm going to be 92. But we even got 2 more years, so we'll be good until I'm 94. But so, you know, I think it's going to happen. That's
Yeah, I mean, there are other people working on it.
tons, but no one's working on lithium sulfur. We have all the intellectual property on lithium sulfur. Now there are people who say it'll never work. It's too energetic. It's too whatever it is. You know, no one else has been able to do. But we have. So I think it's going to work.
As far as the planet as a whole is concerned, are you optimistic or not?
As a citizen of the world, I see pretty good social progress around the world. I see the Chinese and the Indian economies growing very fast. These were countries, that's 40% or 35% of the world, which 10 years ago was pretty submerged and now is coming out. So
Absolutely. Although the populations are growing fast.
the populations are growing fast, but they really are making great progress, and I think that's great. I think that's great. So soon, maybe in my lifetime, a substantial majority of the world will be not third world. Third world will really be a minority. So that's good. Whether we'll blow ourselves up in time, I don't know. Will global warming, climate change be such will catch us unaware and ruin the planet? I don't know. But I'm reasonably optimistic for the world. I think we'll deal with these issues and there'll be enough intelligence. I'm less optimistic for the United States. I'm not optimistic for the United States. I think we have perfected the art of blocking anything. So the way things seem to work, you know, whether it's, I mean, I can't get an awning on my building, this building. You know, oh, no, you see, you have to go before the board of, what do you call it, I don't know what you call it, these buildings that are historic sites, a historic site. I don't know whatever happened here. That makes it an historic site, but it's a historic site, and they don't allow awnings unless special permission, and well, it takes 6 months to get permission to have an awning. I mean, you know, so we've perfected the art of inaction, and I don't see anything really changing. I don't see leadership emerging that is going to propel us in an effective way into this century. Right now, all the thought is our debt is too big. Okay, our debt is too big. You know, the biggest debt we ever had relative to GNP was when? You know,
I guess in World War II.
Right after World War II, it was considerably bigger relative to GDP, whatever you call it, than it is today. Well, we must have paid off that debt, right? Wrong. We never paid off a penny. We grew the denominator. So the numerator, which was very big, stayed, and the denominator got bigger and bigger, and after 10, 15 years, that ratio was right back in the box. We grew the economy. But we're not thinking about that now.
Well, is it possible some crisis could change things?
I don't see it. I don't know what crisis could change things. I mean, we want to pay down the debt. We don't want to invest in infrastructure. We don't want to invest in serious education, which is part of infrastructure. I mean, I just don't see it. It's so depressing. But maybe we'll get better leadership, and maybe something good will happen. But right now,
do you think you have any role you could play?
No.
But you're wrong.
So.
By now, you're, let's say, more well-known than you once were. For example, you have this long list of impressive achievements. You've made a lot of money, which people tend to respect. You're very articulate, amusing, etc. Forceful, logical.
Go on Saturday Night Live, you think, for example?
That's it. Yeah, is there something, as a wise elder statesman who cracks a lot of jokes and so on, whatever, by saying these things enough and in a public enough way, is it conceivable that people might listen for whatever non-intrinsic or intrinsic reason?
I can't say it's impossible that that could be effective, but I'm not very optimistic that I could make that. I haven't really given it much thought. What could I do to make that difference on that scale? I don't know. It's the problems are so pervasive. The parties are so at each other's throats, worse than it's ever been, in terms of politics first, politics second, politics third, policy fourth, maybe.
Yeah. I agree with that.
And so how do you break that kind of a logjam? How do you get people focused on reality and not Tea Party kind of stuff? I don't know. And there are people who go on the air, and there are smart people who say this and that, maybe even amuse people, but I don't know how much people are really going to be moved by such a performance or series of performances. I mean, this guy Friedman, he writes these books. He says we're falling apart. Look at China. We have to do this. We have to do that. He's a pretty good writer. He puts out these books. The world is flat, or the world is square, whatever it is. Is it making any difference? Not discernibly. Why would I make such a difference?
The two of you are rather different. I mean,
yes, he's a good writer.
I don't know.
He's a good writer.
Well, you're a good writer.
Well,
you're a funny guy.
Yeah. I'll take this up with myself.
Yes, please do that.
All right.
Report back to me. So this was when you testified before
Waxman.
Before Congress.
That's right. Before Congress. It was in 2009, I believe, in the wake of everything, and it was just before the election. And he decided to get the 5 top hedge fund guys to testify in his committee, and he just took the list of who made the most money. There's something, and I was on the list, and George Soros that year was on the list, and this one and that one. There were 5 of us. And this was a time, shortly before the election, people were trying to score all kinds of points. There were some awful such hearings where people were really excoriated. Now, the fact is that the hedge funds had very little to do with this, if anything. But it's always fun to beat up on rich people, especially in front of a television audience that will include your constituents. So I was very nervous about this. I didn't want to be excoriated, but I was asked to appear, and I was going to appear. And we started preparing. But Soros said no. Soros said, I will appear, but after the election, not before. And as soon as I heard that, I said, me too. You're not going to get me up here until after the election. And then everyone raised their hand and said, me too. So they agreed to hold it off until after the election, because they weren't going to get their band of, they could subpoena us all, but that's getting ugly and so on. I guess they didn't want to do that. So say, okay, after the election. And I really thought that would be the end of it, because I thought, since once the election was passed, what's the point of putting on the show? But in fact, they did, and it appeared they were trying to gather information. They were not rough. I was prepared for anything. I was prepared for the worst treatment. And I had two lawyers, and they were training me, and I was practicing. Oh, if they ask this, you can say that, but if they then follow up with this, you have to back up with that, and so on and so forth. My head was swimming in what I should and shouldn't do, or could or couldn't say, and so on. I was. They say, "Oh, you're a very rich man, Mr. Simons. Exactly how much did you report as income in last year?" I don't want to talk about how much I reported as income. None of their business. Income tax is your own business. So or there were a million directions they could have followed, which I would have found intrusive and inappropriate. So I had to be taught how to. Well, if they ask that, then you can say this, and so on and so forth. Anyway, we went in there prepared to be excoriated, and we weren't. And I was blessed by having George Soros on my right, because the way they did it, they wouldn't go down the line. They'd pose a question, and then they'd say, "Okay, what do you think, Mr. Soros? What do you think? What do you think?" And so on. George Soros likes to talk. So when they start with him, he'd go on and on and on and on and on, and finally he would stop, and it was my turn, and because I hoped he would talk so long they'd drop the question altogether and so on, but he didn't. And then I could say something, and I had the record for the shortest answer, which was yes, following a great lecture by George, and I just said yes, and they liked that. So, but they were nice to us, and then afterwards.
Why do you think that was? Were they impressed?
I think they didn't want to offend some people, many of whom were political supporters. I mean, we backed some of their efforts at times. The election was over, and maybe they really did want to learn something. It's hard to say. And I worked hard. I wrote you're supposed to have a written statement, which you don't necessarily have to follow, but you're supposed to submit a written statement, which I did, and it was a good statement, and it appeared on the web. But I was so glad that was over. I was so glad.
I remember one thing that you said, which I thought was very good, and that was that they should make an effort to keep people in their homes.
Yeah, that was the first thing I said. We haven't done a good job at that. The banks are sitting with these mortgages, which they haven't necessarily written down yet. They're not so eager to do that, so things linger, and then the mortgages are what I would call in weak hands. But if the banks were to sell their mortgages to you or me, we'd buy them at 20 cents on the dollar. Then we go to the homeowner, and now we're in good shape. You could pay us back at the rate of 30 cents on the dollar. I make 50% on my investment, and he gets his thing cut. Now the bank takes a shellacking, but the bank had taken the shellacking anyway. It was all just sort of pushing it off and pretending, and we're doing a lot of pushing off and pretending. So I figured the banks ought to be dealt with, get that paper into strong hands, and then the owners of the paper can then negotiate with the homeowners and make deals. Sometimes they take the deal, and sometimes they don't, or they walk away, or they don't want to do that. But at least you give people a chance. And usually you can, keep them in their homes. I thought that was very important, but we really haven't done that. And there's all this stuff in foreclosure, and it's the best thing for a house.
So is the problem really that the banks don't want to do it?
The banks are not eager, because it means having to write this piece of paper down and thus showing their balance sheet goes down. So the banks aren't really eager to do it. They're being pushed to do it. That was my idea, keep people in their homes, but we didn't do a good job at that. So I always believe in taking, if it's going to be a hit, take it, and then go on about your business. But sometimes you just want to keep pushing it out into the future, which, sometimes is good.